In this video, we will continue analyzing the structure which we created in Revit in the robot structure analysis. So as I showed in previous video, we will just transfer the file to robot, the analytical model of the Revit file to robot, and it appears here. All elements are transferred. There is a report which you can view if you wish. And we go now to robot and carry on from robot further analysis. First of all, so there are actually 5 things that need to be done now. Six parts of the before just analyzing. First thing was that the supports have not transferred, although we had foundations. These foundations have not transferred as supports in robots, so we can just add supports now. The easiest way is to look at the node numbers, and we can see that the bottoms of columns have node numbers from 22 to 30. So if I go to supports, pinned, and right here 22 to 30 and apply. It placed the pinned support, so that's the first thing, adding support. Next thing is we have all these beams and columns, but they are fixed by default, so we want to make them pinned. And the way to do it is to go to geometry, releases, pinned, and just here in the selection we can choose members all, and that is going to select all the members. You see all are appearing in blue, and we apply. So this is because in practice we normally assume that our beams and columns are simply are pinned at the end. Depends actually on the structure, but in this one we can assume that. So this was second, releases of beams. Next one is to look at the slab, and first we want to change its calculation model. So if you go to geometry, properties, panel calculation model, the slab is currently modeled as shell. So if you click on the new, this is the default one, finite element analysis. We don't want finite element. We want to analyze our slab as one-way slab. You can name it whatever you want, the calculation model. So make sure you tick no finite elements and simplified model method with the triangular and trapezoidal, which is basically one way, assuming one-way slab. Add and close. And we need to apply this one-way slab that we created to our panel, which is basically we have just one floor, so just this one. And now that we have applied, the load will be transferred just in one direction, and that will be the shorter direction. And that is the next step. This will be step 4, which is to check if panel direction has transferred correctly from Revit. You have an idea that I already checked that it hasn't. So if you go to geometry, properties, local panel direction, so this is showing which way our slab is working, and it's working in the blue arrow way. So this is not the correct one. We need to turn it to be in the actual Y direction. So to do that, we tick here and make it in the Y direction vector, which is 0, 1, 0, and we apply it to our floor, one or more floors. 30. Apply. So now the blue arrow is correct, facing correctly in the shorter direction of the slabs, and we can close this. So this was fourth step. So this is everything to do with geometry. Now we need to look at, in steps 5 and 6, we need to look at the loads. Unfortunately, I couldn't get the loads to work, which we transferred from Revit. I don't know why. If you can figure out, tell me. So when I went to the loads, it showed me that the live load is there, but it just didn't transfer correctly when doing the analysis. So what I have done is deleted it. So I just kept the dead load, which is basically the self-weight of whole structure of all the elements. But everything from live load downwards, I deleted. So including all the loads which we don't have, but they just load cases were transferred automatically by Revit. So what I need to do is now to add this live load now. And I'll call it load case 2, live load, add. And I just define it from load definition, surface, uniform load, and in Z direction it's -3. Add and apply to the panel, which is, we can do it from here. Panels all, we have just that 130, and apply. Close. So unfortunately, I could not get the load from Revit to work. If maybe you can try, and if it works, it's brilliant. And now that was 5th step, and the 6th step in this, before we can do the analysis, is to add the combination, which is the ultimate limit state combination, and we make it by using dead load times 1.35 and live load times 1.5, which are the Eurocode factors. Apply, close, and that is all done. So fingers crossed. When I do now the calculations, it will work. What does this mean? An instability. Instability is because all our members are simply supported or pinned. I'll press escape, and it will do the analysis anyway, so you can see we have no errors, but you have all these instabilities. And that is, we could prevent it if we added some bracing, but for vertical load, we will still get the correct answer, so we don't have to make the structure more complicated, just to have like a simple example. And now that we've done the analysis, we go and review the results. On the diagrams, the first thing to check are the reactions, vertical reactions. Click on descriptions and apply. So these are reactions from the dead load, from the live load, from the combination load, and if you scroll here in the menu underneath to sum of reactions for live load, it's saying it's 648. So that's the total vertical reaction for live load. And we can check it easily because we know the dimensions are 6699, so it's 12 by 18. The area times 3, and we get exactly that. So we know that our live load is applied correctly on the whole surface of this floor. For one floor, yes, it's applied clearly, but if you have more surfaces where the load is applied, you can check it's applied correctly. And now I can go on to do the diagrams. Oops, I first need to switch off the reactions. Oops, okay, now I switched on this too early. Okay, so we want to see the shear force on a secondary beam, on a typical secondary beam, which can be this one, for example. And with this button, I can just see that beam. And Fz, so this is from the combination load. Make sure you choose combination load here. And to see the value, parameters, labels, apply. Okay, so this is our shear force diagram, Fz. To see the bending moment on the secondary beam, My. And we can compare it to the simple hand calculations based on one-way slab load transfer. What else can we see for this secondary beam? We can see the stresses. Clearly too high for this steel, 275 steel. And also the shear stress, Tz. So that's a shear stress. Shear stress follows the shear force diagram, and bending stress, the bending moment diagram. And we can now also see deformation. So this deformation is the total deformation from its original position, 132 millimeters. Quite a lot. Now I'll close this one and choose another beam, which is the primary beam. Again, isolate it using this tool and view it in its window. So I'm going to show the Fz force for the combination load. Again, I need to turn the labels. Okay, so this is the shear force diagram, bending moment diagram. Click normalize, 603. Then again we can check the maximum stress. Just note that positive is compression, so maximum stress would be maximum compressive stress. If you want to show the maximum tensile stress, it would be minimum in robot. And also shear stress. And also you can see the deformation. Deformation on of this beam. Switch it off. And last thing that we need to check is the axial force on our column. So I'll separate the column and show the axial force with the label. So this is the maximum axial force on the column, 610 kilonewtons in the combination, from the combination load. So this completes this example. Thank you for watching.